Last time we learned about these things called elliptic functions, which is a very funny name for something that just means doubly periodic. Functions on a lattice. Functions invariant under translation by a lattice. Lambda is generated by 2 points W1, W2, with W2 over W1 not real. Okay, so these are functions on a torus. Maybe this is W1, maybe this is W2, and over here is W1 plus W2, W plus W2. You can see that. Okay, this is a fundamental domain. D is fundamental domain for this action, for the action of lambda, the lattice on the complex numbers. And we wanted to, so this is doubly periodic. So elliptic functions is doubly periodic functions. Doubly periodic. We proved two theorems. We proved that if f is elliptic and holomorphic, then it's constant. There aren't very many interesting elliptic and holomorphic functions. So if we're thinking about these, they have to be meromorphic. We have to allow for some poles. So this is going to be meromorphic. And then we learned how to construct such. So examples. So the holomorphic ones are an empty, not an empty set, but a not interesting set. Are there any at all that aren't that are meromorphic? So we saw that if you take any function g, which is, for example, rational, and you average, again, number theorists call this averaging. Other people would call it just summing over the lattice. This thing will converge, and will converge absolutely and uniformly on compacta. This converges if, for example, g is a rational function, p over q, where the degree of q, I think I wrote this not quite correctly last time, where the degree of q, let's say 5, is at least the degree of p plus 3. I think I had the plus 3 on the other side. I had minus 3. Okay, whatever. So for example, just to give you a trivial example, one trivial example is 1 over z cubed. P is 1 and q is z cubed. So if you sum 1 over z cubed, that has enough decay so that this series converges absolutely, right? We need any decay strictly greater than z squared, if you recall. That's another example. Another example is, I don't know, z squared minus 17 divided by z to the, I could say 5th, but I could also say 6th, plus 12z to the 4th plus 1, whatever, okay? Any of these choices of the function g, when averaged over the lattice, give us meromorphic. This will give us meromorphic. In particular, the denominator has poles. So we get these meromorphic is meromorphic and elliptic. So we have lots of examples of meromorphic and elliptic functions. Okay. Let's make a little definition. The order of an elliptic f, elliptic with respect to on lambda, with respect to a lattice lambda, the order is the number of poles in a fundamental domain. And of course, the domain also depends on lambda. You give me a different set of you give me just any pair of complex numbers, W1, W2, I get some parallelogram. That parallelogram is a fundamental region. Okay. And by the way, it doesn't have to be the one that goes from 0 to W1 to W2 to W1 plus W2. It could be any translate. I mean, just to, let me make that in green. You could take a little translate like this, and that's also a fundamental domain. Right? It doesn't have to be the one on the lattice. Anything like this will tile by translations. Okay, does that make sense? So the order is the number of poles in a fundamental domain. Okay. Well, we can get, so we know how to get, with these rational functions, we know how to get meromorphic elliptic functions of order. So this example has order at least 3. Okay. Holomorphic would be order 0. There are no poles. This is order 0. So we know how to make examples with order 3. We know how to make examples of 3 or higher. We know how to make examples of order 0. Can we make examples with order 1 and order 2? Order 1, order 2. These are the mysterious orders that we need to investigate. So theorem, there's nothing with order 1. Theorem does not exist F elliptic and order 1. How do we prove such a thing? Well, it's very simple. If F is elliptic, with respect to some, let's say, with respect to a lattice lambda, I'm going to stop writing with respect to the lambda. The lambda is always implied, right? It's like the parameter, like the eccentricity of the ellipse. There's just this constant k floating around, so lambda is always there in the background. If F is elliptic and meromorphic, I mean, elliptic and meromorphic means meromorphic, then look at the integral over the boundary of one of these fundamental domains, 1 over 2 pi I, f of z dz. Okay, and assume no poles on the boundary of the fundamental domain. Why can I assume that there are no poles on the boundary of the fundamental domain? Just translate it if I need to. Right? Just shift the fundamental domain, the choice of fundamental domain. And why can't there be infinitely many poles in the fundamental domain? By the way, are there any elliptic functions that are what can you tell me about the behavior at infinity of elliptic functions? Are they meromorphic at infinity? Why not? First of all, if they were, they would be rational functions, and elliptic functions are not rational functions. But second of all, they have to have poles, and whatever those poles are, those poles translate in every direction. So actually, they have infinitely many poles. They have a limit set of poles at infinity. So elliptic functions are always, note, if they're not constant, let's put it over here. Non-constant implies essential singularity at infinity. Essential at infinity. Just by the way. Does that make sense? The poles translate in every direction. Okay, so again, we can assume there's only finitely many poles, so by wiggling the fundamental domain, we can avoid them all on the boundary. So there are no poles on the boundary of our choice of fundamental domain. And if I integrate over the boundary of a fundamental domain, what will I get? The residue theorem. Yeah, it's the sum over the poles, just those inside the disk, the domain of the residues of F at alpha j. Okay, so the picture is, again, I'm just going to draw some fundamental domain, whatever it looks like. Here's some fundamental domain D. We're integrating over the boundary of D. And there's some number of poles in here. And some number of zeros, but we don't care about zeros. The only thing that integrals like this pick up is the residues. And we get the sum of the residues. That's just the residue theorem. But what is this integral? I claimed this integral. Yeah, you got a guess?
Well, I mean, I read the chapter.
Oh, okay. If someone didn't already read the chapter, can you guess what this integral is going to come out to? Taylor, you got a guess? What do we know about f along this line versus this line?
Since it titles, it's like it's doing the same thing there and there. So
Yes.
they're in opposite
Yes.
places.
Exactly. Such as 0. Okay. So whatever it's doing here, it's doing exactly the same thing, but with the opposite orientation along that boundary component. And the same thing here. Whatever it's doing here, it's doing exactly the same thing there. The values of f are identical along this line as on that line because of periodicity. So the integrals just cancel off. Well, wait a second. So suppose that it's order 1. Suppose that there's only one. Suppose that there's only one alpha I. That means this is a single residue. There's a single pole, and its residue is 0. Can that happen? It can happen for a meromorphic function to have poles and residue 0. For example, the function 1 over z squared is a function with a pole at 0, and then its continuation is plus 0 over z, plus 0 times z, and so on. So this is the residue. The residue is 0. It can happen, but the order has to be more than 1. Exactly. The order of the pole. So it can happen. There's no contradiction with f being, you might say, well, that there can't be any zeros. I'm sorry, there can't be any poles at all. No, there can be, but there have to be at least 2. Either 2 because they cancel out, or 2 at the same location with no remaining residue. Okay, so this, of course, is number of poles with multiplicity, always with multiplicity, and so there can't be a simple pole and nothing else. Okay, therefore, no simple, it can't have, how do I want to say this? Can't have a single simple pole. Okay, so there are no order 1 functions. There are lots and lots of order 3 functions and higher. Order 0 is the constants. What about order 2? Can we have order 2 functions? Let me say one other thing before in generalities, so we have theorems of what can or can't happen, and then we have examples. Let's prove one more theorem. Do I want to prove one more theorem now, or do I want to go straight to the example? Let's go straight to the example. I'll give you the theorem in a second. All right. So question, does there exist some elliptic f of order equal to 2? If you remember the Poincare statement, he says with a double infinity. Weierstrauss comes up with this function with a double infinity as opposed to triple. Triple is easy. Can we come up with a function with a double infinity? So, the naive guess is something like, well, you just sum a function, instead of a g of order 3, like total order -3, like 1 over z cubed, right? The total order is the degree of a rational function, is the degree of the numerator minus the degree of the denominator. So the degree of the denominator, we said, has to be at least 3 more than the degree of the numerator. But could you sum 1 over z squared? Could we sum? Our guess is you take 1 over z squared and shift it by lambda and sum over lambda in lambda. This will not converge absolutely. Does not converge absolutely. Does not converge absolutely. In fact, we saw phenomena like this already. Let's go back to one dimension. We thought about functions like a sum over n in z, if I take a single lattice, and 1 over z plus n. Right? You guys remember this? Looking at a function like this? So this function the nth term for n large, z is fixed. For n large, this looks like the harmonic series. So harmonic series diverges. Harmonic series diverges. Do you remember studying this function? Do you remember what it comes out to? Something like pi times cotan. So it turns out that this was, we had this either in class or in homework, pi times cotan of pi z. But we have to make sense of what does this mean? What does this symbol mean? If it was an n squared, there'd be no problem with convergence. The fact that it's an n means it does not, so let's just be clear, this does not converge absolutely. We proved this using Poisson summation, exactly. We had to figure out a way to make sense of this so that we could apply Poisson summation and say something. Yeah, so what can we do with this sum? Well, one idea, so idea one, is interpret the sum, interpret this infinite sum as a symmetric sum. Interpret infinite sum as a limit of symmetric sum. In other words, this infinite sum is equal to a limit as big N goes to infinity, a sum, yeah, you got it, a sum over N being at most capital N of the same thing, 1 over Z plus N. Why would I interpret it like that? Well, once I have a finite sum, now there's no question about how to order things. And I can take this finite sum. Let's separate out the term equals n equals 0. That's just a factor of 1 over z. And then I can group the negative terms and the positive terms. And if I group the negative terms and the positive terms, that's a sum over n, at least 1, of the positive term 1 over z plus n, together with the negative term 1 over z minus n. Right? You guys remember doing this? What's the benefit of putting it like this? Yeah, what is this fraction? Well, let's get a common denominator. What's the common denominator? Z squared minus n squared. And what's the numerator? I multiply by z minus n here. I multiply by z plus n here and add. The n's cancel and I get 2z. So really, what we want to do is not sum this function. So really, we want to replace this function by the function 1 over z plus a sum over n up to infinity now, up to infinity of the function 2z over z squared minus n squared. That has no problem converging, because its nth term is like 1 over n squared, not 1 over n. So this converges absolutely. Converges absolutely and uniformly on compacta. So that's the meaning of, that's one way of making sense of this, this summation. Does that make sense?
When you say making sense, like I could interpret it in a different way. Would I get something that's the same or completely different?
So if what you get, because it's a divergent series, depending on how you choose to order the sums, you can get in the limit any value you want.
Right. So I guess then why do we say that that divergent series is equal to this limit? Like,
right.
It's really not an equality statement at all.
That's right. So it's not this is not a correct equality. That's what the quotes, scare quotes are for. The function cotan pi z is a function, right? It takes values, and it takes the same values as this series takes. But this thing, we have to, we can't just write this function down because it doesn't converge absolutely. So we have to say, how are we interpreting? There's a variety of ways of interpreting it. And if you order, interpreting means which terms do you take when? And if you change your order, yeah, you can, for single values of z, you can get completely different summations. Some will just diverge, some will converge to different values. Okay, but the way you would sort of naturally try to make sense of this thing is, well, what should a sum over all integers would be the limit of a sum over a symmetric sum. If you try to sum all the positive integers and then subtract off all the negative integers, you have infinity minus infinity. There is another way of making sense of this thing. So idea two is to force each term, just like here, the term had quadratic decay when we interpreted it, when we sort of grouped terms. There's another way to get this thing to be, in fact, it'll come out to the same series. But the second idea is to do the following. If you sum over all of the integers, you take this 1 over z plus n, and you subtract off the term 1 over n. Now, okay, that doesn't make sense if n is equal to 0. So let's just take this 1 over z out front, and then take away the 0 term. And let's look at this expression. Okay, what can we say about this expression? Well, again, what do these two things add up to? Let's get a common denominator, which is just n times z plus n. Again, that's quadratic in n. And what happens to the numerator? I get an n over here and a minus z plus n there. So the n's cancel, and I think I get just a minus z. So this is, again, quadratic. This is big O of 1 over n squared. The constant depends on z, but this is as n goes to infinity. So this thing makes complete sense. And now we don't have to think about the order of the summation. I can sum, because this converges absolutely, I can sum in any order. So can sum in any order, not necessarily symmetrically. Does that make sense? And it's idea two that Weierstrauss pursues. So Weierstrauss, so this is like 18, I'm going to make up a number, 70s. Could have been 60s, 80s, I don't remember. Weierstrauss says, let's try to make a function, an elliptic function. He defines this thing called P of z. Of course, it depends on it. There's always the lattice floating around. He defines as a sum over lambda in the lattice, and then 1 over z plus lambda squared minus 1 over lambda squared.
I have a question about idea two.
Yes.
Like, how are you able to subtract off 1 over n without fundamentally changing the sum? Like, you can sum ln of n from 1 to infinity, subtract off the 1 over n, and you get the Euler mesh or only constant. So
yes.
You're changing a divergent series to convergent series.
So I'm just making this series, but notice that if you interpret this, yeah, that's a very, very good question. Haven't I changed things? If you again interpret this sum symmetrically, then I've added a finite amount, and whatever I added for positive n, I've added exactly the same thing with the opposite sign for negative n. So if interpreted symmetrically, if you if you want to worry about the order in which you sum things, if interpreted symmetrically as opposed to arbitrarily, there we go. If interpreted symmetrically, idea two is equal to idea one. You've added and subtracted the same terms at any finite amount. But now you can do this without, the beauty of idea two is that you can stop worrying about the order of summation. Does that make sense? And so that's what Weierstrauss pursues. He says, stop worrying about, okay, lambda equals 0 is going to be a problem here, unless you define 1 over 0 to be 0, as it's defined in interactive theorem provers. So most often you'll see people write this as they isolate the term 1 over z squared, and then they'll sum over lambda in the lattice that are invertible, so not equal to 0, and then this thing 1 over z plus lambda squared minus 1 over lambda squared. Now, wait a second. Does this thing converge? Does this function converge? Bless you. Does that make sense? Am I going too fast? Kaylee, I lost you. Good. Is this too trivial? This is too trivial for a quiz. What is this thing? Let's work this out. Do we indeed have enough decay in order to be able to sum? Remember, we can sum as long as in lambda, this decays faster than 1 over lambda squared. Like 1 over lambda cubed would be perfectly fine. 1 over lambda to the 2.5 as lambda goes out to infinity. Right? So what's the right amount of, what decay are we actually doing when we sum like this? Let's work it out. Okay, so the denominator looks good. I have a lambda squared times a z plus lambda squared. That's growing like lambda to the 4. Right? I have a lambda squared here and a lambda squared there. What's happening to the numerator? I cross multiply, I get a lambda squared minus z plus lambda squared. But what is that? Let's work out the numerator. So the denominator stays the same. The denominator stays the same. Let's say same. And how about the numerator? The lambda squared and the minus lambda squared will cancel. I'll get a minus z squared and a minus 2z lambda. So for large lambda and z not equal to 0, the numerator grows like lambda. And so there's our lambda to the, this is 1 over lambda cubed. Okay, so this series converges absolutely and uniformly on compacta and uniformly on compacta. So we get a holomorphic function or a meromorphic function away from the zeros, the poles rather, the zeros of the denominator. Okay, so we get a meromorphic function. So this P is meromorphic. But now it's not obvious that it's invariant. If I replace no longer obvious is that P of Z plus some element of the lattice is P of Z. Right? We've changed the definition in order to make it absolutely convergent. Why is this thing invariant under the lattice? Well, it wouldn't be a very good definition if it wasn't. So theorem, P is indeed elliptic. Oh, and what's its order? Of order, where are its poles? So here's my domain. Where does this thing have poles? Exactly at the lattice points. When z equals 0, I have a pole. When z equals any lambda, I have a pole. Okay, so z equals 0 is a pole. This is a pole. This is a pole. This is a pole. So if I shift my domain just a little bit, there's a double pole at each of the lattice points. So it's elliptic of order 2. This was our mysterious function that we didn't know immediately how to cook up. Okay, so the ellipticity, all that remains to show, we see that it's meromorphic, it's holomorphic outside of its poles. All that remains to show is that it is indeed translation invariant. So how can we prove such a thing? Well, let's look at the derivative. What's the derivative? It converges absolutely and uniformly on compacta, so we can differentiate term by term. What's the derivative of this term? What's the derivative of z to the minus 2? Negative 2 z to the minus 3. Okay, and then we get a sum over all of the other lattice points, the non-zero lattice points. And what's the derivative of this? Negative 2 over z minus lambda cubed plus 0, plus nothing. A constant, the derivative of the constant is gone. What is this function? We already know this function. It's negative 2 times the sum over G of Z plus lambda, all lambda, where G is equal to 1 over Z cubed. It's one of the ones that we already knew. You see that? If you set G to be 1 over Z cubed, one of our rational functions with denominator having degree 3 more than numerator, then when you sum Z plus lambda, you get 1 over Z plus lambda cubed, summed over all the lattice points, the 0th lattice point and all the others having exactly the same behavior. And then there's a constant factor -2 in front. So this is elliptic. This is elliptic of order 3. Right? Does that make sense? Something else to note. So note that P is P an even or odd function or neither of Z as a function of Z. If I replace Z by -Z, well, this thing doesn't change. This thing does change. But whatever lattice point lambda I have, there's also a lattice point -lambda. And if I replace lambda by -lambda, this doesn't change. And this doesn't change either. So actually, it's completely invariant under Z goes to -Z. So P is easily seen to be an even function of Z. You guys see that? P of Z is equal to P of -Z. And therefore, its derivative is odd. So P prime of Z of -Z is equal to negative P prime of Z. That is odd. Okay, so now consider two functions. Consider f of Z, which is just P of Z, and G of Z, which is P of Z plus some lattice point. I have two functions, f and g. F is just P itself. G is P translated by any lattice point. The derivative of f is equal to P prime. The derivative of G, so G prime of Z is P prime at Z plus lambda 0. But P prime, we know, is elliptic, is doubly periodic. So this is the same thing as P prime of Z by the periodicity of P prime. So f and g have the same derivative. So f minus g, so f minus g has derivative 0. Does that make sense? And all the poles are at the same places with the same residues. So the poles all cancel. So, and holomorphic. And holomorphic. So it's constant. Implies P of Z is equal to P of Z plus lambda 0 plus some constant. All we have to do is figure out what that constant is. Does that make sense? How can we figure out what that constant is? Well, let's look. So let me draw our fundamental domain again. Here's our fundamental domain. Here's W1, here's W2, and here's W1 plus W2. Now, I'm going to look at these half lattice points. Let's look for Z equals, let's say lambda 0 is, let's just prove it for W1. Say lambda 0 is W1. For lambda 0 equals W1. If we can prove that it's invariant under W1 and W2, it's invariant under the whole lattice. Okay, so let's look for lambda equals W1 and Z equals W1 over 2. So in fact, I want to look at Z equals negative W1 over 2. So if Z is equal to negative W1 over 2, I have P of negative W1 over 2. That's this side. What is this side? Z is W1 and Z is negative W1 over 2. Negative W1 over 2. And lambda 0 is W1. So this is P of W1 over 2 plus some constant. So what's the constant? Why?
Because P is even.
P is even. But P is even. But P is even. So C equals 0. Okay, and there's nothing special about W1. So this value, playing the value at negative W1 against over 2, this is negative W1 over 2. This, of course, is W1 over 2. Playing these half lattice values against one another, you see that the function P is elliptic. Therefore, P of Z plus W1 is equal to P of Z. And same for W1 replaced by W2, which implies same for all of lambda. Okay. You will have another proof of periodicity of the double periodicity of P in your homework. You don't have to do it by differentiation. But you get a lot out of this differentiation, actually. Okay, so let me pause there. Any questions on why we have indeed constructed an elliptic function of order 2? So the order 2 is the double pole, exactly at the lattice points. The double infinity, as Poincare put it. And the ellipticity is, we've proved that it's actually invariant under all the lattice points, even though it didn't maybe initially in its definition. Where's it? Here, this is the key definition right here. This is the very, very, very key thing. I'll even double box it. There we go. Now it's special. Okay. So this thing, although it's not immediately obvious why the translation works out. Like if I translate Z by Z plus W, I get a new term here that doesn't come with its own 1 over lambda. Right. And one of these terms looks like a, 1 over Z squared. Anyway, it's not immediately obvious, but we gave a proof for why it is indeed doubly periodic. Okay, there's a lot more that we can get out of this function. This is an amazing function, in fact. Doesn't look it. First, let's prove another general theorem. So, again, we have shown that there are no elliptic functions of order 1. There are no elliptic functions of order 1. We have just shown an elliptic function of order 2, and we already knew elliptic functions of order 3 and higher, and 0 is constants. If F is elliptic of order, let's say n, then F has n poles in D. That's just the definition of order. And let's figure out how many zeros. Zeros in D. How many zeros can F have in D? How can we access poles and zeros? Exactly, the logarithmic, right? Let's do the argument principle. The argument principle is to integrate 1 over 2 pi I times the boundary of a fundamental domain, again, making sure that F has no zeros or poles on the boundary. So wiggle D, so F has no zeros or poles. The boundary of D, the fundamental domain, F prime over Z. And the argument principle says that this is equal to, what's the argument principle? Exactly. Number of zeros, we get a +1 for every 0 with multiplicity, minus number of poles. So far, so good. But what is this integral? Why? Yeah, just like F is periodic, F prime is also periodic, and F prime over F is also periodic. So when you integrate over the bottom, that's the same as integrating over the top, but we're integrating in the opposite direction. And same thing for the two sides. This integral is 0. Done. So how many zeros? If it has n poles in a fundamental domain, how many zeros did it have? Also n. Also n. This is extremely powerful information, it turns out. It turns out. So Let's go back to P prime. What do we know about P prime at these half? Remember, P prime, the derivative is odd. So P prime at this W1 over 2, at this half lattice point, what happens to P prime at W1 over 2? Let's think about negative W1 over 2 over here. Let's say negative W1 over 2. It's odd, so P prime is equal to an odd function is where you have a minus sign. It pulls out negative P of W1 over 2. But it's also invariant under translation by W1. And translation by W1 brings us to W1 over 2. So what? So it's a 0. So P prime has to vanish at W1 over 2. So P prime must vanish, bless you, at W1 over 2. Okay, so again, in our fundamental domain, let's get some colors here. Kaylee, something doesn't make sense. I'm sorry. Thank you. I'm missing a prime here and here. Thank you. I'm talking about P prime. P prime is odd, and it vanishes. It has 3 zeros, all for the same reason. At W1 over 2, at W2 over 2, and at W1 plus W2 over 2, for exactly the same reason. If you look at the negative, I mean, this isn't a very well drawn picture. If you look at the negative of W1 plus W2 over 2, that's over here somewhere. That differs from W1 plus W over 2 by W1 plus W2, which is a lattice element. So it has 3 zeros here. And does it have any poles? P prime has poles at you remember what P prime looks like? It's this 1 over Z cubed function averaged over the lattice. So it has what? Exactly. What kind of 0? Or pole, rather. What kind of pole? Yes. At right there, at 0, has poles at, if I write it with multiplicity, 0, 0, 0. Okay. So this again, this is seeing that the number of poles has to be equal to the number of zeros. We've found all the zeros of P prime. P prime is never 0 again. Does that make sense? So P prime vanishes at the half lattice points and has poles, triple pole at all the lattice points. So if I take for my fundamental domain, if I shift it over just a little bit so that I catch only these 3 half lattice points and 0, then there's no issue with integrating anything on the boundary. Does that make sense? Okay. Well, let's think about P at W1 over 2. Let's just call that E1. Let's think about P at W2 over 2. Let's call that E2. And let's think of P at W1 plus W2 over 2. And let's call that E3. Whatever those are some values, E1, E2, E3, at those center points. So the function P of Z minus E1, my claim is that the function P of Z minus E1 has a double root, double 0 at Z equals W1 over 2. Why? Well, very simple. Let's expand this thing. Let's expand it in a neighborhood of W1 over 2. Okay, so what's its value? Its value at W1 over 2. 0, because the definition of E1 is that, so it's 0. Plus the derivative at W1 over 2 times Z minus W1 over 2, plus higher order stuff. What is the derivative at W1 over 2? 0. But this function, why can't it have more than a double root? Why not more than double root? Does anybody see? Let's see.
What would the derivative of too many zeros?
The P itself would have too many zeros. How many zeros does P have?
Oh, yeah, just 2.
2. It has to have exactly the same number of zeros as poles. P has a double pole at 0 at all the lattice points inside a single fundamental domain. So it can only have 2 zeros. Now, wait a second. P minus E1, E1 is just a constant. So that's still a doubly periodic function. E1 does not contribute any poles. This is still elliptic. This is still elliptic of order 2. So it has 2 poles. The poles are still at Z equals 0. So it can't have more than a double root. This next constant is not 0. The next coefficient is not 0. Does that make sense? You guys see that? Since the number of zeros is equal to the number of poles. In fact, there is no other point in this domain has P of Z equal to Z1, E1, except no other point except W1 over 2 has this. Because not only we know that it has a double root, and it can't have any more roots in the domain. Okay? What does that mean? That means that actually E1, the same is true for E2. E2 is a double root at W2 over 2. And W1 plus W2 over 2 has a double root. E3 is a double root of W1 plus W2 and nowhere else. So that means that E1 and E2 and E3 are all distinct. Okay? So let's look at the function P minus E1 times P minus E2 times P minus E3. What is this function? Let's call this capital F. I claim this is elliptic. F is elliptic. Why? I translate by a lattice point. P doesn't change, and that's the only thing that's there. Of order, what's the order? 6 of order 6. I have a leading term 1 over Z squared here. Leading term meaning how fast does it blow up as I go to 0, where the pole is. So this is like 1 over this near 0 is like 1 over Z squared. This is also like 1 over Z squared, and this is also like 1 over Z squared. So the leading term, so near 0, F of Z is equal to 1 over Z to the 6 plus smaller powers here plus holomorphic parts. Okay, so it's order 6. Does it have 6 zeros? It's got to have 6 zeros if it has 6 poles. Where are they? We just said there's a double zeros at W1 over 2 corresponding to this term. We're multiplying, so we get zeros. We can multiply zeros at W1 over 2, W2 over 2, and W1 plus W2 over 2. Okay? I know another function of order 6. Alternatively, let me make a function g of z, which is p prime of z squared. This is also order 6, right? P prime of z has leading term 1 over z cubed. Actually, it has leading term p prime of z. What's the leading term of p prime? You guys remember? It's not 1 over z cubed. It's negative 2 over z cubed. So this is like negative 2 over z cubed. So the leading term of this is like 4 over z to the 6 plus other stuff. Okay, so it has order 6 pole at 0. And does it have any other zeros? It's got to have 6 zeros. Where are they? Yeah, it has not just poles, but it has simple poles. Simple poles, right? It can't have, these poles can't have multiplicity because it only has an order 3 pole. I'm sorry, simple vanishes, yes, and these are simple zeros. Simple zeros. I'm pointing to the wrong thing. These 3 places where it has zeros must be simple zeros because there's a total of 3 zeros to match the 3 poles. So this function p prime has simple zeros at this thing. So p prime squared has double zeros at each of these locations. Double zeros, order 6 pole at 0, double zeros at w1 over 2, w2 over 2, w1 plus w2 over 2. So we've made 2 functions, f and g. They both have order 6 poles at 0, elliptic of order 6 at 0, all 6 at 0. And they all have double zeros at these 3 things. So the function f over g is elliptic of order 0. We've killed off all the poles and we've killed off all the zeros. They have exactly the same locations of zeros and poles. We've killed them all off. Therefore, f over g is constant. Is constant. That's a 6. That's a g. What constant? Well, what's the leading term of f? 1 over z to the 6. What's the leading term of g? 4 over z to the 6. So the constant, I guess I have f over g. So this is a quarter. So if I multiply by 4 and I multiply by g, we've proved this fantastic theorem. P prime of z squared, that's g, is equal to 4 times f. And f was p of z minus e1 times p of z minus e2 times p of z minus e3. And the e's are all distinct. The ei is distinct. Right, we proved that before. What is this? Let me write this as this equation another way. Y squared is equal to 4 x minus e1, x minus e2, x minus e3. If you have a quadratic in y equals a cubic in x, it's an elliptic curve. That's the definition of an elliptic curve. Why is it called an elliptic curve? Because it's the curve you get from elliptic functions, which are the inverses of elliptic integrals. This is an elliptic curve. And how do you parametrize elliptic curves? You set x equal to p of z, and you set y equal to P prime of Z. P prime of Z. This is a parametrization. It's parametrized. Just like cosine and sine parametrize the circle, this Weierstrauss P function parametrizes elliptic curves. It and its derivative are the thing that you plug in for x and y. And for any value of Z, you'll get, as Z varies, this is the parametrization. You get all solutions to this equation. Elliptic curve is parametrized by P prime. Remember, I promised you, sines and cosines are periodic. Coshes and sinches parametrize x squared minus y squared equals 1. They're also periodic, but in the complex direction. And the parametrization of elliptic curves is doubly periodic. It's these weird transcendental functions that are doubly periodic. Cool? Okay, I think I have time for one more thing. Yeah, I think I can do it. I think I can do it. It's 20 minutes. Moreover, so this is one thing that I promised you, right? Why do these strange P and P, why do the elliptic functions parametrize solutions to elliptic curves? That's why they're called elliptic curves. It has nothing to do with ellipses. Moreover, every elliptic function is a rational function of P and P prime, is a rational function of P and P prime. So if F is elliptic, F is elliptic, then there's some rational function so that R is just a rational function. Ratio of polynomials. P over Q. I can't use P over Q. R over R. U over V. Polynomials U and V. So there's a polynomial in P and a polynomial in P prime. And you take, a polynomial in P and P prime. You take one for the numerator, one for the denominator. Every elliptic function. If you know P, you know every elliptic function. Every elliptic function can be expressed as a rational function, P and P prime. Okay. Why is this true? So this is my claim. In fact, let me make an even stronger claim. So this is claim 1. This is claim 2. Every even elliptic function is a rational function just in P. You only need P prime to make things even. Okay, let's see why this is true. Proof. Does this make sense? What I'm saying? We're moving really fast, but there's, the proofs are all really trivial. So you can get very, very far in this subject without much work.
So with this P function
Yes.
parameterization of the elliptic curve, do we retain any geometric meaning that we would in like the standard elliptic curves in RTL, eccentricity, foci, that kind of thing, or are we not really concerned with that?
So the eccentricity, the analog of eccentricity, right? We have an elliptic curve. There's a parameter K, which, if we make this minor axis or major axis, I don't know if K is bigger or less than 1. If we make one of the axes 1 and the other one K, then the parametrization has the K in it, K cos X and a sine X, right? So the K is implicit in the parametrization. Here, the P, the analog of K is lambda. The lattice itself is implicit in the parametrization. Now you might ask, how does this depend on the choice of lambda? And or the choice of representative for lambda. We'll get to that in a minute. Maybe not today. I'll see how far I can get. So you can say, how does parameterization change with the implicit parameter? There's the parameter. I wrote X. Of course, I want T's. Erase too much. Can I not erase? Okay, I'll try to make this a T. There we go. Okay. So the K, the T is the parameter. Parametrization means give me one variable T so that I can write x and y in terms of that t, and that'll solve, as t varies, that solves the whole equation, right? X squared, what is it? X squared over k squared plus y squared is equal to 1. So an equation in two variables, I have to figure out how one depends on the other. This is a pair of equations with just one variable. I stick in any value of t, and I'll get a solution to that. That's what a parametrization does for you. So in the parametrization, there's an implicit parameter, which is the eccentricity. And in this parametrization of the elliptic curve, there's an implicit parameter, which is the lattice, lambda. Now we can, and the book does, and we also will, maybe not today, have a better way of implementing this lambda so that it's a single complex value. In fact, in a range. But so we'll talk about the space of lattices. We have to understand what's the simplest way we can describe a lattice. We right now are describing it as a pair of complex numbers, W1 and W2. But actually that pair isn't what's essential. There's something else. Their ratio is a complex number. And that's the essential bit. And we'll get to that. Did I answer your question?
Yeah.
Other questions? Does this make sense? Okay. So my claim is that you give me any elliptic function. So we're given f that is even and elliptic on some fixed, again, with respect to some fixed lattice lambda. Because it's even, let's think about f at 0. So f at 0, so at z equals 0, we have three options. F could be regular, or it could have a 0, or it could have a pole. F is either regular, in other words, neither 0 nor a pole. It could have a 0, or it could have a pole. And that 0 or pole has some order. If it's a 0, it has to be an even order 0. Even order. And same thing if it has a pole. It has to have an even order pole. Is that clear? I mean, that's what it means to be. If it's even, if I take an expansion about 0, it only has even exponents in the powers. So whether it starts to the left of the constant term or to the right, it's still going to be even. So far, so good? So what can we do? You see, what we want to do is multiply f by the right shifts and so on of p to get a constant. We know how to get a constant. We get a function with no poles and no zeros. If we kill off the zeros without introducing new zeros, we're in good shape. So f times p to the appropriate exponent is regular at 0. Is regular and non-zero at 0. You agree with me there? Because p has an order 2 pole. P has order 2 pole at 0. So if it had an odd order pole, powers of p wouldn't kill it off. But it has an order 2 pole, so I might need to multiply by p in the numerator. M could be positive or negative. Right? If it has a 0, I kill off the 0 by multiplying it by poles. If it has a pole, I multiply it by zeros. And that 0, so m is equal to negative order over 2. Does that make sense? Okay, so going forward, we can assume, let's just replace this by f. This is our new f. Can assume f doesn't equal 0 at 0, and no pole there either. No pole there. Fine. So now, if we think about what f looks like on a fundamental domain, it's regular here. We can also assume that it's completely regular on this boundary. Well, it doesn't have to be on this boundary. It could be some translate of this boundary. It doesn't really matter. And it has some number of poles. So somewhere it has poles. Yeah, sure, maybe it has some poles on the boundary. And it has some number of zeros. And somewhere there are zeros. Let's see, there have to be the same number of zeros as poles. Okay, what I drew can't happen. Since f is even, if f has a 0 at a in this domain, so let's say this is a 0a, it also must have a 0 must also have a 0 at
minus a.
At minus a.
So it's translated to that.
Exactly, minus a, but translated into to be in the domain. And by the way, if you're in the domain and you just negate, then you wind up in this negative domain. This is negative d. And so what you want to translate by is just W1 plus W2. So the translate here is actually easy to write down, W1 plus W2. So in other words, there's a symmetry. If I have a here, I'll also, oh, I guess I did. So here's negative a, or something equivalent to negative a. This is negative a plus W1 plus W2. Does that make sense? So both of these will be zeros of f if one of them is. But sometimes those two numbers are equivalent. Actually, there's one caveat to this, which is if I'm already on one of these endpoints, if this is a 0, then I don't want to translate by, well, it doesn't matter if I can just translate by like W1 and be back inside, as opposed to, yeah, anyway, I'm not being careful about what's happening on the boundary. It's not so important. So f has zeros at a and negative a. Let's call it negative a, even though it's negative a with a shift. What about the function p of z minus p of a? What do we know about this function? Does this have a 0 at z equals a? Does it have a 0 at z equals negative a? So this also has zeros at z equals a and negative a. Okay, so if we let's call this g of z. Okay, so let's say f, so say f has zeros, and by the way, the same is true for poles, zeros at plus or minus a1, plus or minus a2, possibly with multiplicity. So if a is one of these center points, if a is a half lattice point, then negative a and a are the same point. So it has to have a double root there. But so does p. P also has a double root there, as we already saw, right? That's like the value of E2 or E3, whichever point I'm pointing to. So let G, so if F has zeros at plus or minus A1 through AM, and the order of F will be 2M, right? These zeros are, there's two of them, and poles at B1 plus or minus B1 through plus or minus BM. So it has some number of zeros, it has some number of poles, in fact, the same number, but those come in pairs, positive pairs and negative pairs. So if I let G of Z be the product of P of Z minus P of AJ, J going from 1 to M, divided by the same product in the denominator. So this will have poles at these places. This will have zeros at these places. And this function will have poles at these places. Z, P of Z minus P of BJ. G has same zeros and poles as F. So F over G is holomorphic. It's holomorphic and invariant under translation by the lattice, and hence constant. And we've just written F as a polynomial in P. So f is a rational function in P. Every even elliptic function is a rational function of P. That's what we just proved. Does that make sense? So f is equal to some rational function of P. You just take out where the zeros and the poles are. First, you take out a zero. If there's a zero at zero, you take it out by P itself. And then all the others come in pairs, and you only need half as many. In fact, the rational function is very easy to describe. It's polynomials on top and bottom of degree half of the order of f. F is even, so its order is even. And it's just given by this fraction, where you look at the locations with multiplicity of the zeros of f and the poles of f. It's a very easy function to describe. Completely prescriptive in terms of the zeros and poles of f. Okay? Does that make sense? Now, if f is arbitrary, if f is elliptic and not even or odd, here's what you do. You write f as f even plus f odd, where f even is the evenization of f. You take f of z and add f of negative z, I guess divide by 2. This function's even. F odd is the same thing, except with a minus sign. F of z minus f of minus z over 2. The oddity or oddization, whatever. Right? This is even. So this is a rational function of P by what we just proved. This is odd. So f odd divided by P prime. P prime is also odd. F prime divided by P prime, F odd divided by P prime is even. And hence it's some other rational function R1 of P. And so you put those two together, you only need P prime once, just for the odd part. That implies that F is a rational function of P and P prime itself. So once you have this order 2, it's crucial that this had order 2, as small an order as possible. There is no order 1. There is order 2. That's this Weierstrauss P function. Once you have that order using this even-odd decomposition, you can make any even function out of this order 2 guy. And any odd function, you just divide by P prime, you get an even function. So P and P prime generate, algebraically, all possible elliptic functions. Every elliptic function you could ever write down is a rational function of P and P prime.